Astronomers have just reported the first clear observation of spacetime itself, twisting around a spinning supermassive black hole, exactly as Einstein predicted over a century ago. The announcement came quietly, without fanfare, delivered through the usual channels of scientific journals and observatory press releases, but its implications ripple outward like waves on a still pond. Somewhere in the distant universe, invisible to our naked eyes, and separated from us by gulfs of space so vast that the light we see left its source years before any living human was born, something wobbled. Not a physical object wobbling in the ordinary sense, not a planet knocked off course or a star trembling in its orbit, but spacetime itself, the very fabric of reality, caught in a slow rhythmic twist around one of nature's most extreme objects. The main character of this story is not a person or even a single star, but an event, AT 2020 FGD. The designation is clinical, almost mundane, the kind of alphanumeric label that astronomers assign to thousands of cosmic phenomena each year as automated telescopes sweep the sky. But behind those letters and numbers lies a drama that played out over months and years, a performance staged in the darkness between galaxies, witnessed only through the patient accumulation of faint signals arriving at Earth's doorstep. AT 2020 FD began when a star, wandering through the outskirts of a distant galaxy, drifted too close to the supermassive black hole lurking at that galaxy's heart. What followed was a tidal disruption event, a process both violent and strangely beautiful, where gravity's inexorable pull transforms a stable sun into a stream of glowing gas, a temporary beacon marking the black hole's otherwise invisible presence. This is not a tale of danger. Earth is safe, our sun secure in its orbit around the Milky Way's own central black hole, far enough away that we will never feel the tug of those catastrophic tides. Instead, this is a story about observation and patience, about how scientists trained their instruments on a faint, flickering light source and recognized within its variations a pattern, a gentle, regular wobble that revealed something profound about the nature of gravity and the structure of space and time. The wobble arrived encoded in X-rays and radio waves, invisible to human eyes but crystal clear to the specialized detectors aimed skyward from observatories on Earth and in orbit. Over hundreds of days, as the remnants of the disrupted star swirled around the black hole, astronomers watched the brightness rise and fall in a rhythm, a cosmic metronome ticking out the beat of spacetime's twist. To understand what happened at ACB20 AFD, we must first understand what a tidal disruption event really is, how it unfolds step by careful step across weeks and months of cosmic time. Picture a star, not so different from our own sun perhaps, orbiting peacefully around the centre of its galaxy. For millions or billions of years it follows its path, held in a stable trajectory by the collective gravity of all the mass around it. Other stars, clouds of gas and dust, and at the very centre, the supermassive black hole that anchors the entire system. Most stars never come anywhere near that central monster. Their orbits keep them at safe distances, light years away, where the black hole's gravity is just one component among many, nothing special or threatening. But sometimes, through a chance encounter with another star or a slow migration over cosmic ages, a star's orbit shifts. Perhaps it passes close to a cluster of massive stars whose gravity gives it a small nudge. Perhaps two galaxies merge, and their mingling gravitational fields scatter stars onto new trajectories. Whatever the cause, this particular star found itself drifting inward, falling toward the galactic centre on a path that would take it perilously close to the black hole's domain. As it approached, nothing seemed amiss at first. The star continued to shine, its surface roiling with the same nuclear reactions that had powered it throughout its life, unaware that its structure was about to be tested beyond all limits. The key to what happens next lies in a fundamental fact about gravity. Its strength falls off with distance. Stand twice as far from a massive object, and you feel 1/4 of the gravitational pull. This inverse square relationship governs everything from the orbits of planets to the paths of light itself when it passes near the sun. For a star approaching a black hole, this means that the side of the star facing the black hole experiences a stronger gravitational pull than the far side. Under ordinary circumstances, when a star orbits at a safe distance, this difference is negligible, a tiny imbalance easily absorbed by the star's own internal forces. But as the doomed star fell closer to the black hole in 80, trust FGD's galaxy, the difference grew larger and larger. There comes a point, defined precisely by tidal force calculations, where the gravitational gradient across the star exceeds the star's own gravity, the force that normally holds it together in a spherical ball of plasma. This boundary is called the tidal disruption radius, and when a star crosses it, the black hole's gravity simply wins. The star begins to stretch, pulled into an elongated shape like taffy being drawn between two hands. The stretching accelerates rapidly. Within hours, what was once a sphere becomes a long, thin stream of stellar material. Individual atoms of hydrogen and helium that once formed the star's outer layers now spread along an arc that extends from the black hole out into space. This is the tidal disruption event itself, the moment of shredding. About half of the star's mass, moving with enough velocity to escape the black hole's pull, shoots off into space and is lost forever to the darkness between galaxies. But the other half, the material that was closer to the black hole, or, moving more slowly, falls back. This debris doesn't plunge straight into the black hole. That would be anticlimactic, a quick disappearance leaving nothing to observe. Instead, because the star had some orbital motion when it was disrupted, the returning gas carries angular momentum. It spirals inward, colliding with itself and other streams of infalling material, dissipating its kinetic energy as heat in the process. Over the course of weeks, these collisions build up a structure around the black hole, an accretion disk, a flat spinning pancake of gas that glows brilliantly as friction, and magnetic forces heat it to millions of degrees. The innermost regions of the disk, closest to the black hole, become so hot they emit X-rays, high-energy photons that can only be produced by matter in extreme conditions. Farther out, the disk shines in ultraviolet and visible light, though these are quickly absorbed by dust in the intervening space. The disk is temporary, a transient structure that will last only as long as there is material to feed it, gradually fading as the disrupted star's remains are consumed by the black hole or flung away. A T20-20 AFG was first noticed in 2020, flagged by automated survey telescopes that constantly scan the sky looking for anything that changes: supernova, asteroids, variable stars, or in this case, the sudden brightening of a previously unremarkable point of light in a distant galaxy. The discovery itself was routine. Hundreds of similar events are catalogued each year as our observational capabilities improve and automated systems become more sensitive. But what made a T20 AFHD special was what came after the initial discovery. Instead of simply confirming the event and moving on, as often happens when survey resources are stretched thin, a team of astronomers decided to follow it intensively over months and years. They wanted to watch the entire evolution of the disruption, from the initial flare through the long, slow decline as the disk faded and the black hole settled back into quiescence. This decision to monitor AT2020 AFD for such an extended period turned out to be crucial. In science, many discoveries are made not through brilliant flashes of insight, but through patient accumulation of data, through showing up night after night to take another measurement, to add one more point to a graph that slowly reveals its pattern only after many observations. The team arranged for regular observations from multiple observatories, coordinating schedules and sharing data, building up a timeline that would eventually span hundreds of days. They knew from previous tidal disruption events that interesting physics happens in these systems. The interplay of gravity, magnetism, radiation, and relativity creates conditions that cannot be replicated in any Earth laboratory, but they could not have guessed just how interesting AT-FGD would turn out to be. The distance to AT-FGD is immense, so far that the event we observed in 2020 actually occurred millions of years ago, when early hominids were just beginning to walk upright on Earth. The light and other radiation that told us about the star's destruction had been travelling through space for longer than our species has existed, crossing voids between galaxy clusters, dimming with distance but preserving in its intensity variations a record of what happened near that distant black hole. This is one of the strange gifts of astronomy. We see the universe not as it is now, but as it was in the past, and the farther we look, the deeper into history we peer. The signals from a T2020 FGD arrived at Earth as regular pulses, a pattern in time, and by measuring those pulses with sufficient precision, astronomers could infer what was happening in that distant disk of stellar debris. To understand what the observers found, we need to step back and introduce a prediction that Einstein made, or rather that his theory of general relativity made, about how rotating masses should affect space-time. The prediction is called frame dragging, and it goes by the more technical name of the Lenz-Thirring effect, after Joseph Lenz and Hans Thirring, the two Austrian physicists who first calculated it precisely in 1918. Einstein himself had hinted at the idea even earlier, in 1913, while he was still developing the full equations of general relativity. The basic concept is both simple and profound. According to general relativity, massive objects don't just create a static curvature in space-time, like a bowling ball sitting on a stretched rubber sheet. If a massive object rotates, it should drag space-time around with it, creating a kind of swirling current in the fabric of space and time itself. Imagine space-time as honey, thick and viscous. Now imagine stirring the honey with a spoon. Close to the spoon, the honey swirls rapidly, caught in the spoon's rotation. Farther away, the effect diminishes, but you can still see traces of the circular motion even at some distance from the spoon itself. Frame dragging works similarly, though the analogy breaks down in some ways since space-time is not a fluid in the conventional sense. A spinning black hole is like a spoon stirring the honey of space-time, and anything orbiting near the black hole finds itself caught in that swirl, forced to wobble or precess in ways it wouldn't if space-time was static. The effect is tiny for most everyday objects. Earth's rotation produces frame dragging, but the twist it creates is so small that detecting it required satellite experiments of extraordinary precision. The Gravity Probe B mission, launched in 2004, carried gyroscopes into orbit and measured the tiny precession of their spin axes caused by Earth's frame dragging. The effect was just 39 milliseconds per year, less than the width of a human hair seen from a mile away, but it was there, exactly as Einstein predicted. For black holes, however, the story changes dramatically. Black holes are by far the most compact objects in the universe, packing enormous mass into a tiny volume, and they can spin at incredible rates, with their surfaces rotating at significant fractions of the speed of light. This combination of extreme mass and rapid rotation amplifies frame dragging from a subtle correction into a dominant effect that shapes the behaviour of everything in the black hole's vicinity. The challenge for astronomers has always been that black holes, despite their dramatic effects, are maddeningly difficult to observe directly. They emit no light of their own. Their presence must be inferred from how they affect their surroundings, the motions of nearby stars, the behaviour of accreting gas, the bending of light passing close to them. Measuring frame dragging around a black hole requires observing something that orbits or moves very close to the event horizon, where the effect is strongest, and tracking its motion with enough precision to detect the wobble that frame dragging induces. For decades, astronomers had only indirect hints of frame dragging in black hole systems, suggestions in the data that could be explained in multiple ways. AT2020 AFHD would provide something much clearer. After AT2020 AFHD was discovered, the observing team turned two of astronomy's most powerful instruments toward it. The first was NASA's Neil Gehrels Swift Observatory, a space telescope launched in 2004 and named for an astronomer who had been a driving force in high-energy astrophysics. Swift was designed to detect gamma-ray bursts, the most violent explosions in the universe, but its suite of instruments makes it equally valuable for studying other energetic phenomena like tidal disruption events. Swift carries an X-ray telescope that can observe the hot inner regions of accretion disks, where gas reaches temperatures of millions of degrees and emits high-energy photons that would be absorbed by Earth's atmosphere if observed from the ground. The second instrument was the Carl G. Jansky Very Large Array, or VLA, a collection of radio telescopes spread across the plains of New Mexico. Unlike X-ray telescopes that must operate in space, radio telescopes work perfectly well on Earth's surface because radio waves pass through the atmosphere largely unimpeded. The VLA consists of 27 individual dishes, each 82 feet across, arranged in a Y-shaped configuration that can be reconfigured to optimize different kinds of observations. By combining the signals from all these dishes, the VLA functions as a single radio telescope with extraordinary resolution and sensitivity, able to detect faint radio emissions from the most distant corners of the universe. Why observe AT-2020 FD in both X-rays and radio waves? Because different wavelengths reveal different parts of the system. The X-rays trace the innermost accretion disk, the region where gas spirals closest to the black hole before crossing the point of no return. This disk is geometrically thin, flattened structure whose inner edge hovers just a few times farther from the black hole's centre than the event horizon itself. Here, gravity is so strong that orbital velocities approach the speed of light, and relativistic effects dominate. The radio waves, on the other hand, come from something different. A jet, a narrow beam of plasma launched from the vicinity of the black hole and fired outward at tremendous velocities. Many accreting black holes produce jets, though the exact mechanism remains one of astrophysics' active research questions. The leading theories suggest that jets are powered by magnetic fields that thread through the inner accretion disk, extracting energy from the disk's rotation, or even from the black hole's spin itself, and channeling it into collimated outflows of particles. By watching AT-2020 FD for many months, the astronomers did not just collect isolated snapshots. They built up a detailed timeline, a light curve showing how the brightness changed over time in both X-rays and radio waves. This kind of monitoring requires dedication and careful coordination. Observatories like Swift have many demands on their time. Securing regular observations of a single target over many months means making the case that the science justifies the investment. The VLA similarly juggles numerous projects, and setting aside telescope time for repeated observations of one tidal disruption event is not done lightly. But the team persisted, and as the data accumulated, a pattern began to emerge. When the scientists analysed the light curves, plotting brightness against time for both X-rays and radio emissions, they found something remarkable, a repeating pattern. Both signals showed regular variations, rising and falling in intensity with a period of approximately 20 days. This was not random noise or simple flickering of the sort that accreting black holes often display. It was too regular, too persistent, showing up clearly in statistical analyses designed to detect periodic signals. The technical term for this kind of behaviour is a quasi-periodic oscillation, or QPO, quasi, because the period is not perfectly constant, showing slight variations from cycle to cycle, but periodic because the same basic rhythm repeats again and again. QPOs have been observed before in black hole systems, particularly in stellar mass black holes that accrete matter from companion stars in binary systems. In those cases, QPOs in X-ray emissions are thought to reveal the orbital period of material spiralling through the innermost stable circular orbit around the black hole, or to reflect oscillations in the accretion flow driven by instabilities or resonances. But AT-2020 FD's 20-day oscillation was unusual for a tidal disruption event. Previous TDEs that had been studied in detail typically showed relatively steady radio emissions, perhaps varying slowly over weeks as the jet evolved, but not displaying the kind of short-term regular variations seen here. The key insight came from comparing the X-ray and radio variations directly. When the team aligned the light curves, they found that the oscillations were nearly synchronized. When the X-ray emission brightened, the radio emission brightened too, and when the X-rays dimmed, the radio followed suit. The exact timing showed some lag between the two signals, but they clearly tracked each other, rising and falling together on that same 20-day beat. This synchronization suggested that whatever was causing the variations affected both the inner accretion disk, source of the X-rays, and the jet, source of the radio emission, in a coordinated way. Think about what this means. The inner accretion disk is a region perhaps a few light hours across, so hot and dense that atoms are stripped of their electrons and radiation pressure is intense enough to compete with gravity. The jet, by contrast, extends outward for thousands or millions of light years, a tenuous stream of plasma moving at close to the speed of light. These are very different environments, separated by vast scales in both size and density. Yet somehow they were varying together, keeping time with each other through hundreds of days of observation. The simplest explanation, the one that fits best with our understanding of how black hole accretion systems work, is that there was a single underlying mechanism driving both variations, something that affected the inner disk and the jet simultaneously because they were physically connected. This is where frame dragging enters the story. Imagine the inner accretion disk is tilted with respect to the black hole's spin axis. This tilt could arise naturally during the formation of the disk, as streams of disrupted stellar material collide and settle into a rotating structure that doesn't necessarily align with the black hole's own rotation. Now, if the black hole is spinning rapidly, it drags space-time around with it, creating a swirling current. The tilted disk finds itself embedded in this swirling space-time, and frame dragging exerts a torque on the disk, trying to twist it back toward alignment with the black hole's spin axis. The result is precession, just as a spinning top, tilted at an angle, wobbles or precesses around the vertical direction rather than falling over immediately. The tilted accretion disk precesses around the black hole's spin axis. The inner parts of the disk, closest to the black hole where frame dragging is strongest, precess more rapidly than the outer parts. This differential precession can warp the disk, bending it into a complex twisted shape, but on average the inner disk wobbles with a characteristic period determined by the strength of the frame dragging effect, which in turn depends on the black hole's mass and spin rate. If the jet is anchored to the inner accretion disk, launched by magnetic fields that thread through the disk near the black hole, then the jet should wobble too. As the inner disk precesses, the base of the jet precesses with it, causing the jet to sweep out a cone in space rather than pointing in a fixed direction. From Earth's perspective, this wobbling jet means that sometimes we are looking more directly down the jet's axis, where relativistic beaming effects make the emission appear brighter, and sometimes we are viewing it more from the side, where it appears dimmer. The result is a periodic variation in the radio emission we detect, with a period matching the precession period of the inner disk. The same precession can also affect the X-ray emission. As the inner disk wobbles, the orientation of its hottest regions relative to our line of sight changes. General relativity predicts that a disk's emission will be boosted or dimmed depending on whether the emitting material is moving toward us or away from us, an effect called Doppler boosting or relativistic beaming. If one side of the disk is moving toward us, its light is blue shifted and appears brighter. The other side, moving away, is red shifted and dimmer. As the disk precesses and these motions sweep around, we see a corresponding variation in the total X-ray flux we receive. This disk jet co-precession, driven by frame dragging, offered a natural explanation for AT&T 2020 AFHD's synchronized 20-day variations. When the team ran detailed models calculating what precession period would be expected for a disk around a supermassive black hole of the mass estimated for AT's 2020 AFHD's host galaxy, they found excellent agreement with the observed 20-day signal. The numbers worked. The precession rate predicted by the lens-thirring effect, given the black hole's properties inferred from the galaxy's characteristics, matched the wobble seen in the data. This was not just a qualitative agreement. The quantitative match was precise enough to rule out alternative explanations that didn't invoke frame dragging. Alternative explanations certainly exist for quasi-periodic oscillations in accreting black holes, and the team carefully considered them. Perhaps the 20-day signal reflected some instability in the accretion flow, a pattern in how material spiraled inward. Perhaps it was related to the orbital period of a particularly dense clump of material circling the black hole. Perhaps it arose from some resonance between different parts of the disk. But none of these alternatives could easily explain why both X-rays and radio emissions, originating from such different regions, would vary together with nearly identical periods. Frame dragging, on the other hand, naturally produces co-precession because it acts on the space-time itself, affecting anything orbiting or anchored near the black hole in a coordinated way. This is not just an indirect hint or a suggestive correlation. The detection of disk-jet co-precession over many cycles, with brightness variations tracked precisely over hundreds of days, represents the clearest observational evidence yet that space-time is being twisted by a black hole's spin. Previous observations of other black hole systems had suggested precession, but they typically relied on less direct indicators, changes in spectral features over long timescales, or modelling of more chaotic variability. AT 2020's AFHD provided a clean repeating signal, a rhythm that could be measured and compared against theoretical predictions with confidence. The wobble revealed not just the existence of frame dragging, but also specific properties of the black hole itself. The precession period depends on several factors: the black hole's mass, which determines the overall strength of its gravitational field, its spin rate, which controls how rapidly it drags spacetime around, and the radius at which the inner disk sits, which determines how strongly it feels the frame dragging effect. By combining the observed 20-day period with independent estimates of the black hole's mass from its host galaxy's properties, the team could constrain the black hole's spin. The results suggested that AT2020 AFG's black hole was spinning rapidly, but not at the absolute maximum rate allowed by general relativity. In relativity, there is a theoretical upper limit to how fast a black hole can spin, corresponding to a specific dimensionless spin parameter. A black hole at this maximum spin is sometimes called an extremal black hole, and it has unusual properties. Its event horizon and innermost stable orbit coincide, and frame dragging effects reach their peak. Most black holes are thought to spin at rates somewhat below this maximum, their spins determined by the complex history of how they grew through mergers and accretion over cosmic time. AT2020 AFHD's black hole fit this expectation, with a spin parameter indicating robust rotation but not an extreme case. The connection between disk and jet that AT2020 AFHD revealed also has broader implications for our understanding of how jets are launched. Jets from black holes are among the most powerful phenomena in the universe, capable of extending for millions of light years and influencing the evolution of entire galaxies. Yet the exact mechanism that produces them remains incompletely understood. We know that magnetic fields play a crucial role, but how those fields are generated, how they tap the black hole's rotational energy, or the disk's gravitational energy, and how they collimate plasma into narrow beams are all active areas of research. The fact that AT2020 AFHD's jet precessed in lockstep with its inner accretion disk strongly suggests that the jet is tightly anchored to the innermost regions of the accretion flow. This is consistent with models in which the jet is launched by magnetic fields that thread through the disk very close to the black hole, possibly within the region where frame dragging is most significant. Some theories propose that frame dragging itself helps to twist and amplify magnetic fields, creating the conditions necessary for jet formation. AT2020's AFHD's co-precession offers observational support for these ideas, showing that the jet's behavior is intimately tied to the dynamics of the inner disk, and, by extension, to the twisting of spacetime around the spinning black hole. As the observations continued, another interesting feature emerged. The 20-day beat did not last forever. Over the course of roughly a year, the amplitude of the variations gradually decreased. The disk and jet were still there, still emitting X-rays and radio waves, but the periodic wobble faded, becoming harder to detect as the months passed. Eventually, perhaps after about a year or slightly longer, the regular variations ceased, leaving only a slowly declining, relatively steady emission as the system continued to fade toward quiescence. This gradual disappearance of the precession signal is itself informative. It suggests that something about the system changed over time, altering the conditions that produced the wobble. One likely explanation is that the structure of the accretion disk evolved as the disrupted star's material was consumed. In the early stages, when the disk was dense and geometrically thick with a substantial tilt relative to the black hole's spin axis, frame dragging could exert a strong torque, producing clear precession. But as the disk thinned out, as material was either swallowed by the black hole or expelled in winds and jets, the disk's structure would change. It might become more aligned with the black hole's spin axis as frame dragging gradually warped it, or it might thin to the point where the precession became less coherent, damped by the disk's changing internal dynamics. Think of it as space-time's music gradually fading, the wobble slowing and quieting as the temporary structure that allowed it to be seen dissolved back into a simpler configuration. The tidal disruption event created a transient laboratory for observing frame dragging, a brief window when a tilted, actively precessing disk existed around the black hole. Once the fuel ran out and the disk settled or dissipated, the show ended. The black hole returned to its usual state, spinning silently in the dark, its frame-dragging effect still there, but no longer producing the synchronized variations that allowed it to be detected. Placing this result in historical context reveals just how significant it is. Einstein published his general theory of relativity in 1915, and almost immediately physicists began exploring its predictions. Some predictions could be tested relatively quickly. The bending of starlight by the sun's gravity, confirmed during a solar eclipse in 1919, or the precession of Mercury's orbit, which general relativity explained perfectly. But frame dragging, arising from the rotation of massive objects, was always going to be harder to detect. The effect is subtle for slowly rotating or low-mass objects, and in 1918, when Lenz and Thirring first calculated it, there was no prospect of measuring it, experimentally. For decades, frame dragging remained a theoretical curiosity, a prediction that seemed impossible to test. The necessary precision wasn't available, and the objects where the effect would be strongest, spinning black holes, were barely understood and impossible to observe. It wasn't until the satellite era, and particularly the dedicated experiments like Gravity Probe B in the early 21st century, that frame dragging was confirmed around Earth. That confirmation was important, showing that Einstein's theory worked even in this subtle regime, but Earth's frame dragging is so weak it has no practical consequences for anything orbiting our planet. Black holes offered a different story. Around a spinning supermassive black hole, frame dragging is not a tiny correction but a dominant effect, shaping the behaviour of accretion disks and jets, potentially playing a key role in how black holes grow and how they influence their surroundings. Yet observing frame dragging around black holes proved maddeningly difficult. Astronomers saw hints, certain spectral features in X-ray emissions that could be explained by precessing disks, long-term changes in jet directions that might reflect precession, correlations in variability that suggested coordinated wobbles. But these hints were always indirect, requiring extensive modelling and relying on assumptions about how black hole systems work. AT 2020 FD changed that. Here was a system where the precession signal was clear, regular, and persistent enough to be tracked over many cycles. The synchronization between X-ray and radio variations provided strong evidence that both the disk and jet were precessing together, exactly as frame dragging would predict. The quantitative agreement between the observed 20-day period and the theoretical calculation for Lenz-Thirring precession, given the black hole's estimated mass and inferred spin, was compelling. This was not a marginal detection or a suggestive trend. It was a robust signal that matched the predictions of general relativity in a regime of extreme gravity where the theory could finally be tested directly. General relativity has passed every test thrown at it over more than a century. From solar system scales to cosmological distances, from weak gravitational fields to the vicinity of black holes, the theory has proven correct again and again. Gravitational waves, predicted by Einstein in 1916, and detected for the first time in 2015 by the LIGO and Virgo collaborations, provided another dramatic confirmation, showing that spacetime can ripple and carry energy across the universe exactly as the equations predict. AT 2020 AFHD's wobble adds to this unbroken string of successes, showing that even in the twisted spacetime near a spinning black hole, where gravity is so strong that it drags space and time into a whirlpool, Einstein's century-old theory remains our best guide to how the universe works. It is worth emphasizing that this result does not overturn or challenge our understanding of gravity. Sometimes in science, new observations reveal phenomena that don't fit existing theories, forcing physicists to modify their ideas or develop entirely new frameworks. The discovery that the universe's expansion is accelerating, for example, led to the introduction of dark energy, a component that Einstein's original theory did not anticipate. But 1820 does the opposite. It quietly strengthens our confidence in general relativity, showing that the theory works precisely as expected, even in conditions far more extreme than Einstein or his contemporaries could have imagined testing. The wobble is not a surprise or an anomaly. It is exactly what the theory predicts should happen, and the observation's main contribution is to remove any lingering doubt that frame dragging truly occurs around spinning black holes. Beyond confirming frame dragging, AT 2022 AFHD demonstrates a new technique for studying supermassive black holes. Most supermassive black holes are fantastically distant, small enough on the sky that even our best telescopes cannot resolve their immediate surroundings. Only the Event Horizon Telescope, a global network of radio dishes working together to create an Earth-sized virtual telescope, has managed to image the shadows of black holes directly, and even then only for the very nearest supermassive black holes in the sky. For the vast majority of black holes, we must rely on indirect methods, inferring their properties from how they affect material around them. Watching for quasi-periodic oscillations like AT 2026 FD's 20-day wobble offers a powerful new tool. If future surveys discover more tidal disruption events that show similar co-precessing disks and jets, Each one becomes a natural laboratory where frame dragging can be studied in detail. By comparing precession periods across many events, astronomers can start to map out the distribution of black hole spins, addressing fundamental questions about how these objects grow and evolve. Do most supermassive black holes spin rapidly, or are slow rotators common? Does the spin rate correlate with the black hole's mass or the properties of its host galaxy? These questions bear on the history of black hole growth, whether it proceeds mainly through smooth accretion that spins black holes up, or through chaotic mergers that can spin them down. The technique also offers a way to probe the connection between accretion disks and jets more generally. One of the outstanding questions in black hole astrophysics is why some accreting black holes produce powerful jets while others do not. Spin is thought to play a role. Rapidly spinning black holes might be more efficient at launching jets because frame dragging helps twist and amplify magnetic fields. But the details remain uncertain. By studying systems like AT-13-13-TIDAD, where coprecession directly reveals the link between disk and jet, astronomers can test models of jet formation and refine our understanding of how black holes convert accreted matter into energetic outflows. Looking to the future, new observatories and surveys will likely discover many more tidal disruption events. Projects like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, set to begin operations soon, will scan the sky repeatedly, detecting transient events at an unprecedented rate. Among the thousands of TDs that will be found in the coming years, some fraction should display the kind of synchronized variability seen in AT-2020FG. Follow-up observations with facilities like SWIFT, the VLA, and next-generation X-ray and radio telescopes will allow each event to be studied in detail, building up a statistical sample of precessing disks. Each new event will be another quiet experiment in extreme physics, a natural laboratory running automatically in the distant universe, while we simply tune in our instruments and listen. The black holes themselves are oblivious to our scrutiny, spinning as they have for millions or billions of years, dragging space-time into their whirlpools with no regard for whether anyone is watching. The disrupted stars are long gone, their material either consumed or scattered, the brief flares of light they produced now faded beyond detection. But the patterns they left behind, encoded in the timings and brightnesses of X-rays and radio waves, carry information about the structure of space-time itself, ready to be decoded by patient observation and careful analysis. There is something almost meditative about the image of AT-13-13-TIDAD's wobble, a 20-day rhythm playing out over months in the distant darkness. While we go about our daily lives, while we sleep and wake and sleep again, those faint signals arrive at Earth's doorstep, each photon a messenger from a place where space-time itself flows like a river. The rhythm is slow, gentle, nothing like the frantic ticking of a clock or the rapid beating of a heart. 20 days per cycle, the disk and jet rising and falling together, the black holes spin, twisting space-time in a patient, inexorable spiral. Imagine a quiet night, late enough that the sounds of the day have faded, early enough that the world still holds its breath before dawn. Somewhere overhead, beyond the atmosphere, invisible to every sense humans possess except through the intermediary of our instruments, the faint afterglow of AT-13-13-FD flickers. The event itself occurred so long ago that its light has been travelling longer than our civilization has existed. The black hole at its centre is so distant we could never visit it, even in the wildest dreams of future technology. Yet we can observe its effects, can measure the wobble it creates, can use that wobble to confirm what Einstein predicted a century ago about the nature of space and time. This is the quiet miracle of astronomy. The universe performs experiments for us, naturally creating conditions that we could never reproduce in terrestrial laboratories, and all we must do is watch carefully, accumulate enough data, and think hard about what the data might mean. AT-2020F required no particle accelerators, no billion-dollar research facilities beyond the telescopes we had already built for other purposes. It simply happened, as these events must happen countless times across the universe, and we were fortunate enough to catch it, to recognize its significance, and to study it long enough that the pattern emerged from the noise. A star was torn apart, its material forming a temporary disk around a supermassive black hole. That disk, tilted relative to the black hole's spin, felt the twist of space-time being dragged around by the black hole's rotation. The disk precessed, wobbling like a top, and the jet anchored to it wobbled as well. For roughly a year, we watched that wobble play out in the variations of X-ray and radio light, a cosmic metronome ticking in 20-day intervals. Then, as the disk thinned and the material was consumed, the signal faded, the wobble slowed and quieted, and the system settled back into obscurity. What remains is the knowledge, one more piece of evidence added to the mounting pile that confirms our understanding of how gravity works. Einstein would likely have been pleased, but perhaps not surprised. He had tremendous confidence in his theory, confident enough to declare that if experiments disagreed with general relativity, the experiments must be wrong. That confidence has proven justified again and again, most recently in the slow wobble detected by astronomers watching a distant tidal disruption event. The theory holds. Spacetime behaves as Einstein imagined, bending around mass, rippling when massive objects collide, and yes, twisting when massive objects spin. As you prepare for sleep tonight, consider that dance of spacetime and matter still continues, though we can no longer see 80-120-10 particular wobble. Other black holes spin, other disks form and precess, other jets sweep through space in slow, patient arcs. The universe is full of these phenomena, playing out on scales we can barely fathom, in places we will never visit, yet accessible to us through the light that reaches our eyes and our instruments. The wobble of space-time around a spinning black hole is not something to fear or be alarmed by. It is simply another aspect of how reality works, elegant and precise, following rules laid down by the equations of general relativity. Let that thought settle as your breathing slows. Somewhere in the darkness, black holes spin. Space-time flows around them, twisted into gentle whirlpools by their rotation. Occasionally a star wanders too close, is torn apart, and for a brief cosmic moment the resulting disk and jet wobble together, revealing the underlying twist to anyone watching carefully enough. The pattern is there, regular and rhythmic, a 20-day beat that speaks of frame dragging and lens-thurring precession, and all. The subtle predictions of a theory formulated a century ago by a physicist working with nothing but mathematics and imagination. The cosmic wobble slows and quiets in the mind as sleep approaches, a gentle rhythm that asks nothing of us except that we notice it, that we think about it, that we appreciate the universe's willingness to show us its workings if we only look carefully enough. While we sleep, the black holes continue spinning, space-time continues flowing, and somewhere, perhaps, another star drifts too close, beginning the whole cycle again. The universe is patient, performing its experiments on timescales that dwarf human lifetimes, waiting for us to develop the instruments and the insight to understand what we're seeing. 80-20-20 AFD's message has been received and decoded. Spacetime wobbles when twisted by a spinning black hole, exactly as Einstein predicted. The observation is complete, the papers have been published, the data archived. The wobble itself has faded from view as the disk that produced it dispersed, but the knowledge remains, another thread woven into our ever-growing understanding of the cosmos. And that is enough. That is more than enough. As consciousness fades towards sleep, let the image linger, a distant wobble in the dark, a rhythm in space-time, a confirmation that the universe plays by rules we can understand, written in a language of mathematics and light, patiently waiting across billions of years and light years to tell us its secrets. The wobble slows, the breathing slows. Sleep comes, while somewhere overhead, invisible and serene, the universe continues its slow dance. The next story is about to begin. Please relax and enjoy. A quiet night, anywhere on Earth. You look up and see a scattering of stars, faint pinpricks against the dark. The sky seems still, unchanging, as if the universe has always been this way and always will be. But far beyond anything your eye can see, far beyond the reach of even the most powerful backyard telescope, something extraordinary is happening. 8 to 9 billion light-years away, a black hole weighing tens of millions of times more than our sun is racing through space at nearly 1,000,000 miles per hour, leaving behind it a glowing trail of newborn stars that stretches twice the width of our entire galaxy. This is not a story of destruction or catastrophe. It is a story of motion, of gravity's surprising consequences, and of how patient observation can finally confirm ideas that lived for decades only in equations and simulations. It is the story of a runaway heart, a supermassive black hole that broke free from its home galaxy and now wanders the space between worlds, writing its own luminous signature across the cosmos. For most of the history of astronomy, scientists believed that the massive black holes at the centres of galaxies were essentially fixed in place. Every large galaxy, as far as we could tell, had a supermassive black hole at its core, a gravitational anchor millions or billions of times the mass of the Sun. These objects shape the orbits of stars around them, heat the gas that spirals inward, and sometimes power brilliant jets of radiation that blaze across intergalactic space. They are the hearts of galaxies, and for a long time we assumed those hearts stayed put. Galaxies might collide, merge, and reshape themselves over hundreds of millions of years, but their central black holes would eventually settle down together at the new centre of mass, locked in place by the combined gravity of billions of stars. The idea that one of these enormous objects could be kicked out entirely, sent careening into the void like a stone from a slingshot, seemed plausible in theory, but difficult to prove. And then, in December 2025, astronomers announced that they had done exactly that. Using the James Webb Space Telescope, they confirmed the first clear example of a runaway supermassive black hole, a galactic heart torn from its home and set loose in the space between galaxies. The setting for this discovery is a strange and beautiful pair of galaxies whose light has travelled across most of the age of the universe to reach us. When astronomers first imaged this system with space telescopes like Hubble and later JWST, they noticed something striking. The two galaxies appeared as overlapping rings, their circular arcs of stars and gas arranged in a pattern that looked, to some observers, like a pair of wide, staring eyes. Someone nicknamed the system the Cosmic Owl, and the name stuck. Others called it the Infinity Galaxy, because when viewed from certain angles the overlapping rings resembled the symbol for infinity, that looping figure 8 that mathematicians use to represent endlessness. Both names capture something of the system's character, a sense of looking back at us across the gulf of space and time, a sense of cycles and loops and connections that stretch beyond easy comprehension. Ring galaxies are not common, but they are not entirely rare either. They form when one galaxy passes through another, triggering a ripple of star formation that expands outward in a circular wave, like the ripples on a pond when you toss in a stone. Over tens or hundreds of millions of years, these ripples can produce distinct rings of bright young stars, tracing the path of the disturbance through the gas and dust of the colliding galaxies. The Cosmic Owl is a particularly dramatic example, with two prominent rings that overlap and interact, evidence of a complex gravitational dance between multiple galaxies. When we look at this system, we are seeing it as it was 8 to 9 billion years ago, when the universe was less than half its current age. The light that reaches our telescopes left the Cosmic Owl long before our Sun or Earth existed, carrying with it a frozen snapshot of a collision that unfolded over timescales far longer than any human lifetime. And it was in this ancient, distant system that astronomers noticed something odd. A long, straight streak of light, stretching along one side of the Cosmic Owl like a scratch across a photograph. The feature was thin and linear, running for roughly 200,000 light-years, about twice the diameter of the Milky Way. It was unlike the curved arcs and rings produced by normal galaxy collisions. It looked, in fact, more like a wake, the kind of trail you might see behind a boat moving through water or a jet moving through the sky, leaving a contrail of condensed vapour in its path. But this was not water or air. This was the thin, diffuse gas that fills the space between and within galaxies, and something had ploughed through it with enough speed and mass to compress that gas, shock it, and trigger the birth of new stars all along a narrow ruler straight line. For years this feature was a puzzle. Early observations suggested it might be evidence of something moving through the gas, but what? The most exciting possibility was a runaway supermassive black hole, an object so massive that its passage would disturb the surrounding medium, creating a bow shock at its leading edge and leaving behind a wake of compressed gas where stars could form. But other explanations were possible. Perhaps it was just an unusual stream of gas, shaped by tidal forces during the galaxy collision. Perhaps it was a misidentified arm of one of the ring galaxies, stretched out by rotation or gravitational torques. Astronomers debated the possibilities, but without more detailed data, the streak remained ambiguous, a tantalizing hint without a definitive answer. To understand what makes this discovery so significant, it helps to step back and consider what a supermassive black hole actually is. Black holes come in different sizes. The smallest are stellar mass black holes, the remnants of massive stars that have exhausted their nuclear fuel and collapsed under their own gravity. These objects typically weigh anywhere from a few times the mass of the Sun up to perhaps a few dozen solar masses. They form in supernova explosions, the violent deaths of stars, and they are scattered throughout galaxies wherever massive stars have lived and died. But supermassive black holes are a different beast entirely. They weigh millions or even billions of times the mass of the Sun, and they reside not in the scattered debris of stellar explosions, but at the very centres of galaxies, where they exert a profound influence on everything around them. How supermassive black holes form is still a matter of active research, but we know they must have grown over billions of years by swallowing gas, dust, and occasionally entire stars, and by merging with other black holes during galaxy collisions. The gravity near a supermassive black hole is so intense that it warps space and time itself, bending the paths of light and matter in ways that can only be described using Einstein's general relativity. Material that falls towards such an object doesn't just disappear quietly. It forms a swirling disk, an accretion disk, where friction and magnetic fields heat the gas to millions of degrees, causing it to glow brightly across the electromagnetic spectrum. Some supermassive black holes are surrounded by these brilliant disks, which can outshine entire galaxies, while others are quieter, lurking in darkness with only the motion of nearby stars to betray their presence. Astronomers infer the existence of supermassive black holes, not by seeing them directly. After all, the black hole itself emits no light, but by watching how matter and light behave in their vicinity. Stars near the centre of the Milky Way, for example, have been tracked for decades as they orbit an invisible point at speeds that reach a significant fraction of the speed of light. The only explanation for such rapid motion is the presence of a black hole weighing about 4 million times the mass of the Sun, sitting right at the galactic centre. Similar measurements in other galaxies reveal similar central black holes. Their mass is correlated with the overall mass of the galaxy's central bulge. It seems that galaxies and their central black holes grow together, feeding off the same supply of gas and stars, locked in a relationship that shapes both over cosmic time. Given how massive these objects are, and how central they are to the structure of galaxies, it might seem impossible for them to go anywhere. The combined gravity of billions of stars should hold a supermassive black hole firmly in place, the way the Sun holds the planets in their orbits. And indeed, under normal circumstances, that's exactly what happens. A supermassive black hole at the centre of a quiet, isolated galaxy will stay put, anchored by the gravitational potential well created by all the surrounding matter. But galaxies are not always quiet and isolated. They collide, they merge, and when they do, their central black holes are drawn together, spiralling inward over hundreds of millions of years until they meet at the centre of the newly merged galaxy. And it is in these violent, chaotic encounters that the rare and surprising phenomenon of a runaway black hole can occur. The idea that supermassive black holes could be ejected from galaxies is not new. Theorists have been predicting it for decades, working out the physics in computer simulations and mathematical models. Two main mechanisms have been proposed, both of which rely on the complex gravitational interactions that happen when galaxies merge. The first is what's sometimes called a three-body slingshot. Imagine not two, but three supermassive black holes interacting in the same galactic centre. This can happen when multiple galaxies merge in quick succession, or when a galaxy that has already undergone one merger collides with another before its two central black holes have had time to settle down. In such a scenario, the three black holes orbit each other in a chaotic dance, their mutual gravitational pulls tugging and yanking in ways that can become unstable. Under the right circumstances, one of the black holes can be flung outward, gaining enough speed to escape the gravitational pull of the galaxy entirely. It's a cosmic version of the slingshot effect that space missions use to gain speed by swinging past planets. Except here, there are no careful trajectories or planned burns, just the raw, chaotic dynamics of three enormous masses interacting in close quarters. The second mechanism is gravitational wave recoil. When two supermassive black holes spiral together and finally merge, they don't just combine their masses, they emit gravitational waves, ripples in the fabric of spacetime itself, travelling outward at the speed of light and carrying away energy and momentum. If those gravitational waves are emitted symmetrically in all directions, the merged black hole stays put, its centre of mass unchanged. But if the waves are stronger in one direction than another, which can happen if the two original black holes have different masses or if they are spinning in certain ways, the merged black hole will recoil, kicked in the opposite direction, like a gun recoiling when it fires a bullet. The amount of kick depends on the details of the merger, but simulations suggest it can be substantial, potentially reaching speeds of thousands of kilometers per second, more than enough to escape even a massive galaxy's gravitational pull. For a long time, these ideas remained largely theoretical. Astronomers suspected that runaway supermassive black holes should exist somewhere out there in the universe, wandering the space between galaxies or moving through galactic halos far from their original homes. But finding them was another matter. A black hole on its own emits no light, and even a supermassive one, millions of times the mass of the Sun, is effectively invisible against the vast backdrop of space. To detect a runaway black hole, astronomers would need to catch it in the act of interacting with something, ploughing through gas, for example, or dragging along a disk of accreting material that glows as it heats up. Even then, distinguishing a runaway black hole from other astrophysical phenomena would require careful measurements of motion, mass, and the surrounding environment. It was a needle in a haystack problem, and for decades, the needles remained hidden. The cosmic owl changed that, when the James Webb Space Telescope turned its powerful infrared instruments toward the tip of that long, puzzling streak of light. It was able to do something earlier telescopes could not: measure in exquisite detail how the gas in that region was moving and how its light was shifted by motion and heating. JWST's ENIA-SPEC integral field spectrograph is a remarkable piece of technology. It doesn't just take a picture or capture a spectrum of a single point. It divides a small patch of sky into thousands of tiny regions, obtaining a complete spectrum for each one, mapping out the velocity, temperature, and chemical composition of the gas across the entire area. This kind of data is extraordinarily rich, and in the case of the cosmic owl it revealed something unmistakable. At the tip of the linear feature, the gas showed a sharp change in velocity, about 600 kilometers per second across a region only about 1 kiloparsec wide, roughly 3,200 light-years. That's a dramatic shift, far too abrupt to be explained by normal galactic rotation or the gentle flows of gas in a merging system. The data suggested that the gas was being shocked, compressed by something moving through it faster than the speed of sound in that medium. When an object moves through a fluid faster than sound waves can travel in that fluid, it creates a shock wave, a sudden jump in pressure and temperature as the fluid piles up ahead of the moving object. We see this on Earth when a jet breaks the sound barrier, creating a sonic boom. In space, the same physics applies to objects moving through the thin gas that fills galaxies and the space between them. By modelling the observed velocity shifts and the structure of the shock, the astronomers who analysed the JWST data were able to infer the properties of the object creating it. The black hole itself, they concluded, was moving at roughly 950 to 1,000 kilometers per second, around 2.2 million miles per hour. That's fast enough to cross the distance from Earth to the Moon in about 6 minutes. The mass, based on the strength of the shock and the dynamics of the surrounding gas, was estimated at a minimum of 10 million times the mass of the Sun, possibly more. These numbers fit perfectly with what you would expect from a runaway supermassive black hole. Massive enough to plough through the intergalactic medium without being deflected, fast enough to escape the gravitational pull of its home galaxy, and creating a bow shock at its leading edge where gas is compressed and heated. This was the confirmation astronomers had been waiting for. The combination of high speed, large mass, and a clear bow shock signature matched the predictions from simulations and theory. The long linear feature wasn't just a stream of gas shaped by tidal forces. It was the wake of a runaway supermassive black hole, the first such object to be unambiguously identified and studied in detail. The JWST observations turned a decades-old hypothesis into a confirmed reality, giving scientists their first solid example of a galactic heart torn loose and set adrift. And that wake, that long straight trail of light, turned out to be even more interesting than just a signature of motion. When astronomers examined it more closely, they found that it wasn't just compressed gas. It was a stellar nursery, a thin string of star-forming regions stretching across 200,000 light-years. The gas compressed by the black hole's bow shock had cooled and collapsed under its own gravity, fragmenting into dense clumps where new stars were being born. Observations showed that these stars were young and blue, their intense ultraviolet light ionizing the surrounding gas and making it glow. The wake was, in effect, a galaxy-scale contrail, a visible record of the black hole's passage written in the light of newborn suns. Imagine it, a supermassive black hole, invisible itself, but leaving behind a glowing thread of stars like breadcrumbs dropped along a path. The stars farther back in the trail formed earlier, closer to the moment when the black hole was first ejected from its home. The stars near the tip formed more recently, as the black hole continued its journey and compressed fresh gas in its path. The wake is a timeline, a natural record of the black hole's motion over millions of years. By measuring the length of the trail, the ages of the stars within it, and the speed of the black hole, astronomers can estimate how long ago the ejection event occurred. The wake becomes a kind of cosmic clock, ticking off the passage of time in units of light years and stellar lifetimes. This is one of the most poetic aspects of the discovery. In astronomy, we're used to the idea that light carries information about the past. Every photon that reaches our telescopes is a messenger from another time, showing us the universe as it once was. But the runaway black hole's wake takes this a step further. It is not just a frozen snapshot, but a dynamic record, a trail that shows change and motion over time, preserved in the luminous aftermath of the black hole's passage. It is a story written in starlight, and we are only beginning to read it. But what caused this ejection in the first place? Why is there a supermassive black hole racing through the cosmic owl instead of sitting quietly at the centre of one of its galaxies? The answer almost certainly lies in the violent gravitational interactions that occur during galaxy mergers. The cosmic owl, remember, is not a single galaxy but a pair of ring galaxies, clearly in the process of colliding and interacting. When galaxies merge, their central black holes are drawn together, spiralling inward as dynamical friction, interactions with stars and gas, drains away their orbital energy. Eventually the two black holes come close enough that their mutual gravitational attraction dominates, and they enter a tight binary orbit. If left alone, such a binary would slowly lose energy by emitting gravitational waves, eventually merging into a single, more massive black hole. But if a third black hole enters the picture before that merger happens, perhaps brought in by another galaxy colliding with the system, the dynamics change. The three-body problem in physics is notoriously chaotic, with outcomes that depend sensitively on the exact starting conditions. In simulations of triple black hole systems, researchers have found that one black hole is often ejected at high speed, while the other two remain bound and eventually merge. The ejected black hole carries away momentum and energy, a consequence of the complex gravitational interplay among the three objects. This is the three-body slingshot scenario, and it is one plausible explanation for the runaway black hole in the cosmic owl. The other possibility is gravitational wave recoil. If two of the central black holes in the cosmic owl system had already merged, and if that merger was asymmetric enough to produce a strong recoil kick, the resulting merged black hole could have been flung out of the galactic centre. The key is asymmetry. If the two original black holes had different masses, or if they were spinning in certain configurations, the gravitational waves emitted during the merger would be stronger in some directions than others, and the merged black hole would rocket away in the opposite direction. Simulations have shown that recoil velocities can reach several thousand kilometers per second in the most extreme cases, though typical kicks are smaller. The observed velocity of roughly 1,000 kilometers per second is well within the range of what gravitational wave recoil can produce, making this a viable explanation as well. The truth is, we don't yet know for certain which mechanism is responsible. Both are consistent with the observations, and both are consistent with the chaotic, violent environment of a merging galaxy system like the cosmic owl. What we do know is that the black hole has been kicked out, that it is moving at high speed through the gas surrounding the galaxies, and that it is leaving a trail of star formation in its wake. The discovery doesn't just confirm that runaway black holes exist, it also provides a natural laboratory for studying the processes that can eject them, the way they interact with their environment, and the consequences of their motion over millions of years. One of the most exciting implications of this discovery is that it gives astronomers a new way to search for similar objects. If runaway supermassive black holes produce long linear wakes of star formation, then finding more of them may be a matter of looking for these distinctive trails in deep surveys of the sky. The James Webb Space Telescope is now observing the universe in unprecedented detail, mapping distant galaxies and their surroundings with a sensitivity that earlier telescopes could not match. Upcoming missions like the Euclid Space Telescope and NASA's Nancy Grace Roman Space Telescope will survey even larger areas, building up vast catalogues of galaxies across cosmic time. If other runaway black holes are out there, producing similar wakes, these surveys should be able to find them, and finding more examples would be scientifically invaluable. Each runaway black hole is a test case for the theories of black hole mergers and ejections. By measuring their speeds, masses, and the properties of their wakes, astronomers can refine their models of how galaxies and their central black holes evolve over time. They can estimate how often these ejections happen, what fraction of galaxies might have lost their central black holes, and how this affects the growth and structure of galaxies over billions of years. A single example is remarkable, but a population of runaway black holes would open up an entirely new window into the dynamics of galaxy mergers and the fate of the supermassive black holes at their centres. The discovery also changes the mental picture we have of galaxies and their evolution. For decades, the standard model has been that every large galaxy has a supermassive black hole at its centre, and that these black holes grow steadily over time through accretion and mergers. When two galaxies merge, their central black holes merge as well, settling into a new equilibrium at the centre of the combined system. This picture is mostly correct, but the cosmic owl shows that it is not the whole story. In rare cases, a galaxy can lose its central black hole entirely, ejected into the surrounding halo, or even into intergalactic space. The galaxy is left without its heart, at least temporarily. Over time, it may regrow a new central black hole by accreting gas and capturing smaller black holes from its surroundings, but the original has been lost, wandering alone through the cosmos. This adds a layer of complexity and unpredictability to the story of galaxy evolution. Galaxies are not just growing and merging in orderly, predictable ways. They are sometimes losing their most massive central objects, redistributing matter and energy across vast distances, reshaping themselves in response to rare but dramatic events. The universe, it turns out, is not only expanding but also rearranging its contents in subtle, sometimes unexpected ways. Supermassive black holes, once thought to be permanent fixtures at galactic centres, can sometimes break free, leaving behind only a faint trail of stars to mark their passage. There is something quietly profound about this. We're used to thinking of astronomical objects as fixed in their roles. Stars orbit galaxies, galaxies orbit galaxy clusters, black holes sit at the centres of galaxies. But the universe is more fluid than that. Even the heaviest, most massive objects can be moved, can be displaced, can wander. The runaway black hole in the cosmic owl is a reminder that gravity, for all its power, is not always a force of stability. It can also be a force of disruption, capable of flinging even supermassive objects across space, writing new patterns in the distribution of matter and light. The runaway black hole also serves as a kind of natural experiment, revealing aspects of black hole physics and galactic dynamics that are hard to study in any other way. By observing the bow shock at the black hole's leading edge, astronomers can learn about the properties of the intergalactic medium, its density, temperature, and composition. By studying the wake, they can learn about star formation triggered by shocks, a process that may have been important in the early universe when galaxies were first forming and gas was being compressed by collisions and cosmic flows. The runaway black hole is, in effect, a moving laboratory, probing its environment as it travels and leaving behind a record that we can observe and analyse. And it is worth emphasising again that this discovery did not come from a single observation or a single telescope. It is the result of decades of work, building up the technology and the theoretical framework needed to identify and confirm such an object. Early images from Hubble revealed the cosmic owl and its strange linear feature, sparking curiosity and debate. Ground-based telescopes contributed follow-up observations, measuring the light from the streak and hinting at the presence of young stars. Theoretical work provided the context, predicting that runaway black holes should exist and outlining what their signatures might look like. And finally, JWST delivered the detailed spectroscopic data that clinched the case, showing the bow shock and allowing astronomers to measure the black hole's speed and mass with confidence. It is a perfect example of how modern astronomy works: incremental progress, careful observation, and the patient accumulation of evidence over many years, leading at last to a moment of clarity and confirmation. The discovery was announced in December 2025 after rigorous analysis and peer review, and it was met with excitement across the astronomical community. Here, at last, was the first unambiguous example of a runaway supermassive black hole, the confirmation of a phenomenon that had been theorized for decades but never clearly observed. The papers describing the work were posted to the Archive preprint server and published in leading journals, where other scientists could read the details and begin planning follow-up studies. News of the discovery spread through press releases and science journalism, bringing the story to a wider audience. People like you looking up at the night sky and wondering about the hidden motions and dramas unfolding far beyond the reach of human eyes. But for all the excitement, there is also a sense of calm and perspective that comes with this kind of discovery. The runaway black hole in the cosmic owl is not a threat. It is not hurtling toward us, and even if it were, the vast distances involved mean it would take billions of years to cross the space between its galaxy and ours. It is simply there, doing what physics dictates it must do, moving through space, interacting with the gas around it, creating a wake of stars. It does not know we are watching. It does not care. It is a consequence of gravity and motion, playing out on scales that dwarf human concerns, and yet it teaches us something fundamental about the universe we inhabit. It teaches us that even the heaviest objects can be moved. It teaches us that galaxies are not static, eternal structures, but dynamic systems shaped by collisions, mergers, and rare, violent events. It teaches us that patient observation, careful measurement, and the steady accumulation of knowledge can eventually reveal phenomena that once seemed impossible to detect. And it teaches us humility, a reminder that for all we have learned, the universe still holds surprises, still offers up new wonders for those willing to look closely and think deeply about what they see. As you stand under the night sky, or lie in bed thinking about the distant cosmos, it is worth holding that thought. The stars above you are part of a galaxy that, as far as we know, has a supermassive black hole quietly sitting at its centre, holding everything in a delicate gravitational balance. But somewhere out there, in a galaxy system called the Cosmic Owl, a black hole that once held a similar position has broken free, racing through space at nearly 1,000,000 miles per hour, trailing stars in its wake like sparks from a fire. It is a rare event, a cosmic oddity, but it is real, and it is happening right now. Or rather, it was happening 8 to 9 billion years ago, and the light from it is reaching us only now, carrying the news across the vast gulf of space and time. This is the nature of astronomy. We are always looking backward, seeing things not as they are but as they were. The runaway black hole we observe today may have long since slowed, captured by the gravity of another galaxy, or it may still be moving, racing through ever more rarefied gas in the intergalactic void. We cannot know without waiting billions of years for new light to arrive, and of course we will not be here to see it. But that does not diminish the wonder of what we can see now. The wake is there, a 200,000 light-year thread of stars stitched across the fabric of space, a signature written in light and time, waiting for us to notice and understand, and understanding it has required the best tools and minds that humanity can bring to bear. The James Webb Space Telescope, launched after decades of planning and engineering, is one of the most sophisticated instruments ever built, capable of detecting the faint infrared glow of distant galaxies and breaking that light down into spectra that reveal the motion and composition of gas across cosmic distances. The scientists who analyze the data, astronomers, astrophysicists, specialists in black hole dynamics and galaxy evolution, brought years of training and experience to the task, piecing together evidence from multiple observations, building models, running simulations and testing hypotheses until the picture became clear. The discovery is a triumph of human curiosity and ingenuity, a reminder that we are capable of understanding things far removed from our everyday experience, as long as we're willing to look carefully and think rigorously. But it is also a reminder of how much we still do not know. The runaway black hole in the cosmic owl is the first confirmed example, but is it typical? Are there many others out there, or is this an exceptionally rare event? How often do supermassive black holes get ejected during galaxy mergers, and what determines whether they are recaptured or escape entirely? How do galaxies evolve after losing their central black holes, and how long does it take for a new one to form? These are questions that the discovery raises but does not fully answer. They will require more observations, more data, and more time to address. The work has only just begun. In the meantime, the runaway black hole continues its journey, unaware of the attention it has attracted. It does not know that its wake has been measured, its speed calculated, its mass estimated. It does not know that it has become famous, in a small and academic way, among the community of astronomers who study such things. It simply moves, as it has been moving for millions of years, compressing gas, triggering star formation, leaving behind a trail that glows softly in the infrared, a beacon that says something passed this way. And perhaps that is the best way to think about it, not as a violent or dramatic event, but as a quiet signature, a gentle reminder that the universe is full of motion. Galaxies drift through space, stars orbit their centers, planets spin on their axes, and sometimes, very rarely, a supermassive black hole breaks free and wanders, writing its own story across the dark. The story is not one of danger or destruction. It is a story of change, of rare events that reshape the cosmos in subtle ways, of trails left behind that tell us, if we are patient enough to read them, something about how the universe works. The light from the cosmic owl has travelled for 8 to 9 billion years to reach us, crossing distances so vast that they defy easy comprehension. Along the way, the universe has expanded, carrying galaxies apart, stretching the wavelengths of light and shifting it toward the red end of the spectrum. By the time that light enters our telescopes, it has been transformed, its original blue and ultraviolet photons now glowing in the infrared, a warm, invisible glow that only instruments like JWST can detect. But the information is still there, encoded in the light spectrum, in the shifts and patterns that reveal motion, temperature, density. The light carries a message across the ages, and we have finally learned how to read it. And what it tells us is this, that in a distant galaxy system shaped like an owl or an infinity symbol, a supermassive black hole has broken free, leaving behind a trail of stars that stretches across space. The trail is a record of motion, a timeline written in starlight, a natural experiment in black hole physics and star formation. It is confirmation of a phenomenon predicted decades ago, a turning point in our understanding of how galaxies and their central black holes evolve. It is a discovery that will reshape textbooks and simulations, that will inspire new searches and new observations, that will deepen our knowledge of the cosmos in ways we cannot yet fully predict. But it is also, simply, a beautiful and strange fact about the universe we live in. There is a black hole out there, racing through space, trailing stars. It exists, it is real, and now we know about it. That knowledge does not change our daily lives. The stars above us still look the same, the moon still rises and sets, the earth still spins on its axis. But somewhere in the back of your mind, as you look up at the night sky, you can hold the thought, out there, far beyond the reach of the eye, a runaway heart is moving through the dark and we have seen its wake. This is the quiet satisfaction of astronomy, the accumulation of knowledge about things that do not touch us directly, but which enrich our understanding of the universe and our place in it. We will never visit the cosmic owl, never see the runaway black hole up close, never walk among the stars in its wake. The distances are too great, the timescales too long, the technology too far beyond our current reach. But we can observe, we can measure, we can think and calculate and understand. We can add this discovery to the growing catalogue of things we know about the universe, and we can use it to refine our theories, to test our models, to guide our future observations. And perhaps, in some distant future, when our descendants look back at the early 21st century, they will remember this as one of the moments when our picture of the cosmos shifted, when we realised that galaxies are not as stable and permanent as we once thought, when we confirmed that even supermassive black holes can be displaced and set wandering, when we began to appreciate the full dynamism and fluidity of the universe on the larger scales. They will look at the data from JST at the images of the cosmic owl and its glowing wake, and they will see it as we see Galileo's sketches of Jupiter's moons or Hubble's plots of galaxy redshifts, a key piece of evidence that opened a new chapter in our understanding. For now, though, we are living in the moment of discovery, and there is a particular pleasure in that. The papers are fresh, the data newly analysed, the implications still being worked out. Scientists are already planning follow-up observations, searching for other runaway black holes, developing new techniques to identify them in the vast surveys of the sky. Theorists are revisiting their simulations, tweaking parameters, exploring the range of possible ejection mechanisms and the likelihood of each. The discovery has sparked a flurry of activity, a burst of excitement and curiosity that will sustain research in this area for years to come. But the black hole itself, of course, knows none of this. It does not know that it's the first of its kind to be clearly identified, that it has vindicated decades of theoretical predictions, that it has become a subject of intense scientific interest. It simply continues on its path, moving through the gas of the cosmic owl, compressing and heating it, leaving behind a trail of newborn stars. In a few million years, the wake may fade, the stars dispersing or evolving off the main sequence, the signature of the black hole's passage slowly erased by the changing dynamics of the galactic system. Or perhaps the wake will persist, a faint thread visible to future observers as a clue to an ancient event. Either way, the black hole will keep moving, its motion determined by the gravitational kick it received long ago, a consequence of forces and interactions that unfolded in the chaotic heart of a merging galaxy system. And that, perhaps, is the final lesson of the runaway black hole. That the universe is governed by laws, by physics, by the interplay of gravity and motion and energy, but also by chance, by the particular configurations and encounters that happen at particular times and places. The ejection of the black hole was not inevitable. It required a specific set of circumstances, a galaxy merger, multiple black holes in close proximity, the right speeds and angles and masses to produce a strong enough kick. Change any of those factors, and the outcome might have been different. The black hole might have settled at the centre of the merged system, might have formed a binary with another black hole and spiralled inward over millions of years, might have remained a fixed and stable heart for the new galaxy. But that is not what happened. Instead, it was flung outward, set on a trajectory that carried it through space, leaving a luminous trail in its wake. This interplay of law and chance, or of deterministic physics and contingent circumstance, is part of what makes the universe so endlessly fascinating. We can predict the general behaviour of systems, can calculate the probabilities of different outcomes, can understand the mechanisms by which things happen. But the specific details, which galaxy merges with which black holes get ejected and which remain, which trails of stars form and which do not, those depend on the particular history of each system, the unique sequence of events that unfolds over billions of years. The runaway black hole is a result of that history, a product of the cosmic owl's violent past, and it carries within it the memory of events we can only infer and imagine. So as you drift off to sleep, or as you step outside one more time to look up at the stars, let your mind wander to that distant system. Picture, if you can, the overlapping rings of the cosmic owl glowing faintly in the infrared, their arcs of young stars tracing the ripples of a collision that happened billions of years ago. Picture the long, straight streak of light, a thread of stars stretching across 200,000 light-years, each one a sun born in the compressed wake of a passing black hole. And picture the black hole itself, invisible but undeniably real, racing through the gas at nearly 1,000,000 miles per hour, creating a bow shock at its leading edge, writing a story in starlight that we are only now beginning to read. It is a story that speaks to the grandeur and strangeness of the universe, to the power of gravity to shape and reshape matter over cosmic time, to the rare and remarkable events that punctuate the otherwise steady evolution of galaxies. It is a story that confirms ideas imagined decades ago, that opens new avenues of research, that deepens our understanding of the cosmos in ways both practical and profound. But above all, it's a story that reminds us of the universe's quiet, ceaseless motion, the galaxies drifting through space, the stars being born and dying, the black holes wandering between worlds, all of it unfolding on scales that dwarf human comprehension, all of it happening now as you read these words, as you look up at the sky, as you close your eyes and imagine the vast dark distances and the glowing trails left behind by runaway hearts. The next story is about to begin. Please relax and enjoy.